Now let's make things even a little more complex. This time we're going to say there's a relationship between x1 and y, and there's a relationship between x2 and y, but there's no relationship between x1 and y1, or x1 and x2. That they are, in fact, independent of each other, even though they both explain just a little bit of y. For reasons I'll explain in a bit, we'd say this is a case of no collinearity. Right, so here, what's happening? Well, first let's look at our diagram. Now, let me draw that just a little bit bigger so I can get the variance in there just a little bit. Here, x1 explains some of the variance in y, and x2 explains some of the variance in y. Our r squared equation becomes r squared y1 plus r squared y2. This goes to 0, right? Because there's no relationship here between x1 and y, or x1 and x2. That r12 goes to 0. So we leave that out. All over, again, this is 0, so this whole denominator goes to 1. So now, r squared is just equal to the sum of each of the r squareds, right? So r squared of y1 plus r squared for y2. This is when the two are independent of each other, right? And so this shaded area, again, let's call this A, and we'll call this B. So here, the r squared, the percentage of variance explained, is A plus B divided by that entire, I'm just going to call it the entire area rather than giving it a letter. Right, so if we called this E, for reasons I'll call it later, this would be A plus B plus E. Right, but we'll just say over the entire area for the sake of simplicity. Because it's the percentage of variance explained in the whole thing. Now, A and B here are the contributions of each of these variables. Right, so A is the contribution of x1 to y, B is the contribution of x2 to explain the variance in y. In fact, we might look at each of these as the delta r squared for x1 and the delta r squared for x2 are these pieces here, right? Because they're the additional variance in y that are explained by each of those, each contribution of an independent variable.